you guys got some flavor, right? What it is, as I said, that although you need to know quite a few things, but as long as you are not doing hands-on thing, you won't get the full feeling about what the complications are. It will be still in the in this room, and then there is no point. So you have to work it on. Even it's the simple regression when we learned, you can take to these situations where nobody will tell you that fit this type of regression, because that's the type of things data science we are not talking. You will see that how difficult to find a set of variables where you will work for the regression even. Because you have to do number of visualization before you even start doing the model. Okay. So, as we talked about, this first portion, probably the stat people, you can even sleep, take a nap, but you can help me as well. So, what we are going to do as a part of the, as you can see that regression is essentially everywhere. That and regression means that not y equal to x beta. We can write it into y equal to x beta, but it could be completely different thing. But I like to call everything in a regression package. That's what you have seen. So, and today mostly I'll go with some of the classification tools, and which would be related to what I am going to start right here. As you know that classification again is very basically in an hour you will discover that it is nothing but regression when your response variable is a qualitative characteristics. Nothing but, and classification is also nothing but regression when your response variable is a qualitative variables. So that's the thing. So here is a qualitative problem. It's a very generic problem related to the clinical trial. Basically, you know that clinical, to even bring a new drug in the market or the newer version in the market for any drug company, they had to spend billion of dollars, because it goes number of clinical trial, phase 1, phase 2, phase 3, all sorts of things. But what is the bottom line they like to eventually prove by doing thousands of experimentations? What is the improvement, or is the improvement is effective improvement or not, right? So that's essentially they do. Starting from the animals, then they go to the different types of human beings, and that's the way the drug development goes. It's a very complicated procedures, but the statistical understanding behind that is very simple. So all these big stories thought it would be, you can think about new drug, you can think about that there is a new drug here, there was a previous version, and this is the new drug, whether this is effective in terms of cardiovascular disease or not. Okay? So as I said that definitely we don't, when you go really with the clinical trial group, you have to spend quite a few days before you can even get this table. So this table says kind of the effectiveness that new drug with respect to the previous drug. Yes, no, because the cardiovascular disease, did you have the disease or did you have the heart attack or not? That's the answer. So you can see the response is, you cannot collect it as a numeric number. It's a yes, no number. So yes for this older version of the drug, 189, but the newer version drug, the heart attack rates or not rates, so the number reduces, and out of this total number, the question is there any improvement? How do you do that? Very simple question. That's what Ajay said, that after doing so many things, the manager, when this manager of the whole team will make a call, they will just ask you, is this an improvement? Because when you have to convince to the doctor, the government, and like we call the FDA, then the stats team or the data science team is behind. They will try to support that why we think that this is the effective or not. But in eventual things, what we have to do from the statistical standpoint, we have to give a test whether this is effective or not. How do you do that? Simple, very simple, right? Even we have probably the first basic stat class you have learned. What you will do?
Whether you have a disease that you have taken the medicine and the result is you saw the improvement in the next 5 years or maybe.
So basically that's the data, yes or no. Here we can see that the number of incidents actually reduces for this new drug. Although it's by number, this number we cannot really compare because it administered on this plus this many people, this administered this plus this many people. So you have to take the proportion. But what does it mean? Essentially you are calculating a mean here because some of the people who have the here yes divided by total number of people. That's what you will get the proportion. And similarly here the proportion, but essentially is the mean way of calculating the mean of a qualitative variables. That's essentially we are doing, nothing more than that, right? As I said that if you understand the mean, then you understand the whole thing. So essentially, so you are doing the two mean test. And how we will do that? Again, you can do simple t-test type of things, right? But since it is the proportion, so there are quite a few phases would be there. Again, you have to change it to numeric number. Generally, you will do 1, 0, and if this is a typical situation, there is no issue. But we can later on probably I'll give you some examples that it depends on really how the way you are coding. Your coding can change your conclusion completely. But in this type of situation, if you do 1, 0, 0, 1, 1, 0 doesn't matter. So you can do that, and then you calculate the proportion. That yes, that means there was the heart attack for the old drug. That calculation goes the number of people divided by the total number of people, that is about 1% or 1.7%, right? Same way you calculate the new drug. For the aspirin is the new drug. Aspirin is a generic medicine, all of you know. So that is about 0.9%. So when you do the test, essentially you do, there is no exact test available. You do the approximation test based on approximate normality, right? That's what you do. And then test can be done using the confidence interval, like what is the difference between this one and this one. This is kind of the formula you don't need to know. Basically you are looking whether this difference is significant or not. So you calculate this type of interval and then see whether the interval contains 0 or not, right? That's the simple way this formula is given. So the confidence interval comes for this particular data set is this. So by looking this your conclusion, there is a mild evidence that it might improve, because what you see that the confidence interval does not contain 0, but it is very close to 0. So at least you would expect like 0.5% improvement in the old new drug, right? Because that's reduces. So this result is fine. Just a side note, this type of result, if you get this type of number, at least the statistician should give the caution to the manager that they should not believe on the statistician 100%. The reason is that those who derived this formula, it is all approximated formula, and it has to valid only if n is large. And in most cases, the mathematician has no idea how big this n has to be. And as a result, those who are working really in the industry setup, in oftentimes, as I said, that the whole things comes in stage 1, stage 2, stage 3, stage 4, stage 5, and in some stages sample size could be very, very low. As a result, if you do this type of testing, then this may not be valid thing, because this is, anybody has any idea? Now the stat people, the approximation is order of the n inverse. So if n is 15, say, because doing this experiment with 15 human might cost you a lot of money. So they don't allow you to do more than 10, 15 human. that's the final stage of the experimentation. But if it is order of n inverse, that means 1 over 15, that can offset this whole thing even. So as a result, what statistically we are saying that this is right, that may not be right, because our formula we know there is some approximation is there. So that's why sometimes the theoretical understanding is important to give a chance to interpret that this type of result. Oftentimes you should not take it literally and make the policy making decision. You should not do that thing. Anyway, that's a side note. But otherwise, we see some kind of improvement here. That's the way you will do it, right? Another way you can do, there are many different ways to visualize this whole result. As I said that oftentimes to understand better, you have to, same answer you are trying to get, but there is a different way to get the answer as well. So this one is a straightforward textbook type of answer we could do. We could get the answer using the relative measurements, what is called the relative risk. That is actually more popular in terms of common people understanding than the confidence interval or anything. So if you do this relative risk, then you will calculate this one. But here is an example what the relative risk could be. May not be that much effective way of reporting the whole thing. So there is two proportion, say 0.010 to 0.001. That means if the new disease has the heart rate attack is 0.001, you can see some difference because we are the number people, we can see the difference. But you say the common people, when you are selling your drug to the common client, you are saying that, oh, if you take this, the risk is 0.001, and if you do not take this thing, then your higher risk 0.010. Ask 10 people in this room, doesn't matter the 0.001 or 0.01. What does it matter? They would not see much difference in this number, right? But you change it to the relative risk just by ratio, then how we were trying to say that if you take this new drug, the risk of heart disease will less, tenfold less. Then people will think, oh, this is relatively better. So what I am trying to say that in statistics there are different tools are available, and you have to also understand what tools you will be using so that it would be much better interpretable and people can understand. So this is first thing what I am coming from. The previous one is one way of doing the standard statistical way of reporting the thing, but this is the relative risk. If I do the relative risk, you can see the impact of my statement changes by saying this versus by saying this, right? So if you say in this way, definitely you would be able to convince your client much better way that the risk is tenfold less versus risk changes from here to here. Okay? Same way, the relative risk of two proportions is 0.410 versus 0.401. But here you can see the differences probably by number is not that bad. But if you take the relative one, then it is 1.02. So when it is in the very boundary, basically what it is happening, when you are in the boundary sense, then your reporting things should be much more careful. But this one is essentially in the middle, where most of the times we do this middle part, even in terms of when you will do the computations, you will see. So all these things kind of make sense in some way. If you are working with some of these model fitting, etc., and the real value is close to the boundary, although you know that the convergence issue, all this issue arises. But if you're in the middle part, then there is nothing, no problem. Usually your code goes well, but also you can see the implication, some of the implication in terms of when you are delivering the results, that has also some implication from that perspective as well. So now for the aspirin problem, initially from the confidence interval, you got this into 0.00.52 something, right? Now if I go to the relative risk, this becomes 0.0171 divided by, this is the aspirin one, 1.82. What does it mean? What does it mean? I just said, right? If I go with the relative risk, that means the risk of having the aspirin will reduce the risk of heart attack almost about 82%. Just to show, before I go further, remember that this number was 0.05, and that's the way you are trying to convince. And if I try to naively even interpret this one, there is, because you should take the lower bound, that only 0.5% probably the chance that you can have the improvement, right? So nobody is going to buy this your product if you are saying that only 0.5% of this thing, because you cannot give more than 95% of the guarantee if you say a lot more, right? So improvement would be 0.5% risk improvement, right? With confidence, with high confidence. But if I try to say this way, then it is lot more convincing, although the same result I am getting. But this is telling me that relative risk is 82% lower with the new drug compared to the old drug, right? And which is the basically you digging the data a little bit differently so that you can get much more meaningful result. Now, problem would be, yes.
Because of this normal approximation
No, actually it is not. It is essentially how the way you define the parameters. So previously the parameter was theta 1 minus theta 2. It's kind of linear. Now you are actually doing theta 1 divided by theta 2. So it's a function of the parameters. So that is one of the things. And then you can see essentially all relative way. Basically you are changing the scale. As I said that, so that is also oftentimes it is important. So everything has to be measured with some normalized scale. Why you will like to say this thing? Because there is a reason. Sometimes normalized, we always study in statistics that normalized scale give you the better computations. But actually there has lots of other implications. So similarly, when there is a parameter, this one you can think about some kind of standardization of the parameters. So you have in your model some original parameter, but you are deriving the another parameters for the purpose of reporting or your understanding to this the way it gives me better understanding of the problem or better understanding of the data, what data is saying. If you would have done that confidence interval, you couldn't say much more. So you just, that's what you are looking, and then for common understanding, these are better way to understand rather than the confidence interval. But by doing this way, statisticians actually got a new problem. Okay, so this is all we understand from the common people perspective, like they are not statisticians, they think also this is the better, same data, but this tells me much more convincing way that the new drug is better than this thing. But note that parameter has already changed. Instead of pi 1 minus pi 2, it is pi 1 divided by pi 2. Okay? So now the confidence interval calculation is also, you have to redo. This is, since this is so, this whole procedure is so popular in every field, everybody uses, you can actually use SAS proc fric, you get the confidence interval this. But this confidence interval calculation is not so easy. Okay? There is lot more approximation than the previous confidence interval. So, but what is the, for this class purposes, now look at this confidence interval. How do you interpret? So the lower limit is 1.43 of the relative risk, upper limit is 2.30. And what is the interval says? With a high confidence that the risk improvement happening at least 43%, and if you are lucky, you get 230% risk improvement, right? Because this is the upper limit. But at least you can give the guarantee that there is a risk improvement of 43% if you have the new risk, medicine. So completely dramatic way you are changing your statement. Previously your statement was that you might improve in your risk assessment only 0.5% with a very high confidence, 95% confidence or whatever you say. But from the same data now you are saying that your relative risk changes at least 43% if you take the new data set. Okay. So these are all part of when you are doing some data analysis. You need to understand that just running the proc regression or LM not enough. You have to also think about that if I can reparameterize, then can I get different way of saying all these things, and which could be much more meaningful. Then another way of doing these things, something called the odds. Everybody has heard about odds, right? Odd of winning the game. This is the way most of the newspaper write, right? Really nobody write in terms of the proportion, they write the odd. So odd is essentially winning versus not winning, or success versus not success. Now, so you can calculate this odd for the placebo group, the previous drug group, and you can calculate, once you have this proportion, you can calculate the odd for the new drug. Now you can take the ratio, see what, so if you take the ratio, that's called the odd ratio essentially. That is also a popular term used by in the industry essentially. So odd ratio formula, again, it is different. So if I do this odd ratio, then for this aspirin problem, it becomes 1.83. How do you interpret this thing? So you oftentimes you hear this statement that odd of having the not having the aspirin versus having the aspirin is 83% more, or the risk is 83% more, and it is in the odd scale, right? That's the odd you say. Odd of, or when a team is playing to the other team, then you always oftentimes you represent odd of this team winning over the other team is 84% or 182%, something like that, right? So what is that odd? This is this odd you calculate actually. You calculate the odd of one team, odd of the other team, then you take the ratio. That's the way it goes, the odd ratio. So the estimated odds were 83% higher for the placebo. So the higher the odd would be, the better the product would be, or the better the chance would be. So now if I can keep going, so what I tried to show it here, 3 different ways of representing the same analysis. But each time I'm trying to show you the, not only the formula, because this is the point estimate, there is no error or anything. Then if you like to have the confidence interval for this thing, how do you do that? Have anybody, the stat people have done this confidence interval for the odd ratio? No, but these are the very important things the people really want. So, but why I'm showing that? Because each time I'm trying to show that there is a different confidence interval. So you'll get this result, numeric result also differently, but problem from the statistical standpoint is getting more and more complicated to calculate the confidence interval. First thing, you're at step 1, you don't have the exact formula, whatever I have with that approximate formula. Step 2, that approximator getting little worse. And here, it could be even worse. So, but unless, as I said, it is just a good review that how the way people calculate the odd ratio. And since we are in this data science class, I wanted to warn you, whatever we do, these are based on large sample theory. So if you, when you are doing with for small fractions, like you are doing only, say, one team versus other team, one team played only 5 times, another team played only 6 times, these formulas may not be that much valid. Okay. So, understandable, very simple problem, but many different way we could answer. Now what I am trying to go to the next stage, can I do this, solve this problem? Because we have been doing this regression, can I do some kind of regression type of thing and do the same solution? Is it possible? Clear? Because we have seen that regression helps us a lot, right? First thing, why? Because here also I showed you what we are doing. It's the mean estimation, nothing but just doing the mean estimation. And then already I convinced you guys that if you have a regression, particularly effective other variables, then we can improve the mean estimation, right? So at this point, first, how do I frame it in a regression setup? Why we are thinking? Then if I have many more variables which is causing that whether you will have a heart attack or not, then you'll have better estimative and better. But to do that, I have to go for a regression setup that will give me my unified setup, and then I can apply all these least square type of things, all these things. So that's the main idea. So why you would like to take it to the regression setup. So how do you do the regression setup? Everybody is getting my point, right? Where we'd like to move. We like to have it. That's why your final system has to be very well developed, because number of things you will be putting in that system. That same routine you will be calling. Okay, so that's why we have to learn something what is called the logistic regression. Basically, we can put everything in a logistic regression structure. I'll show you. So that's what the logistic regression begins, although it starts with just two proportions, but actually that problem you can formulate completely in a logistic regression form. And what is logistic regression? I'll come in a minute. Essentially, your outcome has two features, again not really quantitative, it's a qualitative features. So that's why it is very much related to the classification. In fact, logistic I'll be using essentially as a classification. But if I have this regression type of setup, then you can explain why the classification is better. So that's why logistic regression is so popular. You can interpret many different dimensions. All right. So what essentially we like to do, again here the pi, that the proportion we calculate, already I said that this is the mean, right? And in a regression, what we try to do, we try to find out the relationship mean with whatever your feature variable, predictor variable. That's what we like to do. That's what we use the notation. It should be function of the x. So if I follow this step by step, I should be finding a model for pi equals to something, right? That's what we have done in regression. The mean equals to beta 0 plus beta 1x plus beta 2x, right? That's what we do. So here also the mean is already, we said that pi x, that's what already we talked about. So I have to find pi x equals to something, right? That's what would be the idea. But what would be the equal to something plus something, or in general way, pi equal to f of x. So what would be that f? That's the question. In a linear model, it is f equal to alpha plus beta x plus beta 2x, all these things. To do this type of things, you have to start thinking about what kind of problem really you'd like to solve. I can talk to the aspirin problem as well, but probably this is even easier. Suppose you are going to make a decision whether you will buy a new cell phone or not. Okay, because every day there is a new phone nowadays. So iPhone 10 is in the market. How much cost here? It is 70,000. So you have one, right? No one.
89,000. It's around 1 lakh with all duties and taxes.
Who else? You have. 6 is anyway. So okay, let's talk. So I'll give 2 examples, right? But there is a tendency of many people, when there is something comes into the market, we have to jump it on, right? I know many people. So, but you have to make a call. So this is a probably it's not deterministic, right? You will be always thinking about whether I'll buy it or not buy it. It's not that you have to pass the exam, that you will definitely pass the exam or do not definitely pass the exam. So how the decision changes, suppose you have an income. So how this, so decision would depend on the income, right? What is your income is, that's what is the, because to have the regression, effective regression, we have to find a feature which should have the influence on my response. Here response is the buying decision and feature is the income. So how does it matter? If your income is, say if you are a celebrity, it doesn't matter whether it is 1 lakh rupees, 2 lakh rupees, doesn't matter, right? It doesn't cost you at all. How about if your income is, costage you said 1 lakh, so if your income is say 5 lakh rupees, then what? Things started, you will be thinking, right? So that means it really does not, the response does not have same impact depending on which value of your features is. But in a linear regression case, we did not think in this way. Every time we just model beta, same beta, beta x. So whatever the x value, x, the feature value is always y equal to beta x. But here I cannot think about in this way, because your decision changes, the risk changes depending on your income. Similarly, if your income is 10,000 rupees, you have decision is pretty much done. Those the group whose income is say 1 lakh to 5 lakh rupees, their decision would be very much depending on, or that's a probabilistic decision they will make. So in other words, what I'm saying, that probability of making a decision that buy is kind of fixed for the very high income group, very low income group. In the middle income group, it changes depending on where your income is. So then if this is the risk in mind, then you have to think about when you are associating your pi to the feature x, x is the income, it cannot be just a linear way, right? So what could be possible way? You can think again, then we have to go back and look at what are the mathematical curve I know which could explain the feature just we discussed, that it does not change much in a very high income, in a very low income, but it changes in the middle income group. If it is a different feature, we have to do it. But this is, let's take only one of this example. So only we understood that this is not a flat curve. It should be a curve which have the characteristics that does not change at the two extreme things, only changes in the middle part, right? So what are the curves we know? Then we go back to the mathematics class and try to understand what are the curves are. So something called the logistic curve, which is we studied in the math class or anyway, where we know the some of the properties, etc. well. Again, it's like a no distribution is normal, but if it looks like normal, then we try to, oh, okay, the bell-shaped curve we studied in as a normal, so that's why you bring the normal. Same way, this one in mathematics literature or in stat literature, very well known. And look at this shape. So this is the pi, and this is the value of your feature. So the pi changes when it is kind of this lower part, that means low income group, almost 0 probability. But if it is a high income group, almost 1 probability. But in the middle income group, the probability changes as the way your income increases, with certain rate, of course. So that means when you are modeling these things, if the data kind of support this type of thing, you can borrow the idea of logistic curve to model that the mean of the y through the logistic thing, and that's why it is called the logistic curve. That's the only reason it's called the logistic curve. Okay, but other type of example that your risk might be other way around, so then you can do this way. Essentially, you call that the S-shaped curve, and what are the main properties are like normal. It is kind of the symmetrical curvature in both way. That's what you'll find. And same thing, if the risk kind of increase over the high value income group, then this beta you will find bigger than 0. If the risk is downsized, then you will get this beta less than 0. So number of properties you can study following this thing. Okay. So very commonly used curve to model this type of phenomena, whatever I just said, is a logistic curve. But there is if you believe that your application, still it is the response is a qualitative variables, which means that you have to do probably 1, 0 or something, but the feature really does not relate in this way, then you should not do the logistic regression. Because we do just because of the convenience. And there is many of the other reasons from the regression perspective. It has a very good interpretation. I could interpret well. And if I write this way, then my mathematical equation should be good. I can prove the consistency. I can write down the iterative equations, many things pretty easily. That's the only reason I do. There is no other reason a data scientist has to use this logistic curve. But nevertheless, like the way we learn the normal distribution or the linear regression under normality, same way you should learn this binary regression, rather I would say, under logistic very well. You have to learn before you go beyond anything. Everybody is clear? Okay. So, as I said, this is a very important model for categorical responses. Rather, I would rather like to write in this way the qualitative responses. Okay, categorical responses, we use the word because that's what our everyday basis understanding. But this is basically you should write as a qualitative response. Even for disease case, when you go, whether you have a disease or not, whether you have a cancer or not. So it's all qualitative characteristics. So initially this is started with much more the biomedical studies, but in social science marketing it is heavily used model in this one. In finance, credit scoring, like you like to estimate the risk. So definitely when you get the loan, the bank is calculating each time the risk depending on your number of risk factors. This could be a huge number of risk factors. Early days, they used to have only few, like your previous history with the bank and maybe your income, 2, 3 factors, that's fine. But nowadays, so much data are there, you can use as many features as possible, and we don't need to talk too much because you can see that we have the tools now to handle this type of thing. Same way we'll go back. Lasho group, Lasho type of things, we will do it if I have the huge number of features. But general way, so that's why it is important first to learn your logistic regression better. Okay? So if you are working in or looking forward to work in the finance or marketing industry, definitely you have to have. Already I said that in the marketing, a company that relies on catalog sales may determine whether to send a catalog to a potential customer by modeling the probability of a sales as a function indices by past buying behavior. But why they need to know? They don't like to send the catalog everyone. The two reasons: it costs you, and another thing is that if it really is not effective, then why should I send this part? Other use, which is indirect, but for the stat people indirect, but as you can see that I have been keep saying it's a direct, heavily used in data mining, classification and discriminant regression, and that's what I'm connecting most of the, I'll come back again with this. But you can see it's essentially for the regression, if I use this thing to predict what I'll get, your y is a qualitative thing, so I have to predict these qualitative characteristics. So what does it mean? The classification, essentially you do these qualitative things. So not really indirect use, rather than I would say that direct use. Okay? So what we said, that the pi, that the mean, this was the mean, that should be the logistic curve. So this is the another representation of the logistic curve, essentially. Okay? And what you do, that take the mean or take the odd. So this is the nothing but the log odd. Remember that pi over 1 minus pi is the odd. So it is the log odd. So another way you might say, in a logistic regression, your linear model, but in the left hand side you have the log odd. instead of the direct mean. Okay, so that's the way you can say. So that's why it is in the odd scale, log odd scale, this is a linear model. And that's why it is oftentimes we call the generalized linear model, because it's a part, you can think about a linear model, but not exactly linear, because in a linear case we do this one equal to this thing. But if I take this type of transformation, and there is a mathematical way people try to explain. If you are in a math class, then what happened? That this belong to minus infinity to plus infinite, pi belong to 0 to 1. So really it does not match the mapping, because 1 to 1 not, it's a 0 1 to minus infinity plus infinite. By making pi 1 minus pi, take the log, then it makes minus infinity to plus infinite left hand side, right hand side go minus infinity to plus infinite. That's the mathematical interpretation. But you understood already why we have to understand other things. Okay? So, and good thing is that whatever at least we have been talking in this class, it has to have a mathematical foundation. So some of this is the mathematical, it is right as well. So, and this is simple thing if you like to write, no. So this is, if this is your risk, once you fit this part, then risks at a value of, new value of x, it is this function you can calculate. So what you'll do, given a data set, you'll fit the data, the algorithm, if I get a chance I'll talk, but you can find least square type of equation, but it won't be exactly closed form expression. You have to do iterative solutions. Okay, and there is number of different algorithms, and one should really write down each of these steps to understand better why it may not converge. Oftentimes you might say that it is not converging. Even R has very good stable routine, but for many data set it may not work. And why it is not, to understand better, you have to understand the whole algorithm. But bottom line is that given a data set, you find out this, so this is your model, this is the parameter, and then when a new person come in, suppose you are calculating the risk, then look at his x value, plugged in here and get that hat, so that the new risk has been calculated. If you think about the classification, that's also you classify in either of the group by looking this part. Okay? I think I will skip this, all this little bit more discussion. Like as I said that basically what I wanted to say, the risk is changing. So what is the beta? Beta is the rate of change in the risk. But that rate of change actually is different at the different group. So oftentimes what is the insurance companies like to know, they classify the group of people in a different groups, like high risk group, low risk group, not really based on that the actual risk, rather the rate of change, that this group of people, how much, what is the rate of change for this income group from here to here. And that's the way most often they classify, rather than just looking the risk. Okay? So, and this curve actually gives you rate of change differently, for rate of change is different for different values of the x, which is sharply different than a linear regression case. Linear, if you do the same problem, by accidentally you will do the linear regression, which I might do it here even. Then what, you may not see apparently there is any mistake, unless you see really absurd result. If your result looks good, you might say okay. But issue is that it really does not give you this type of characteristics. That means risk does not, rate of change in rate of change in the risk does not change with the different values of the your risk factors. So if you do the linear models, then oftentimes you really do not capture the data characteristics well, although your computer code may go through. Okay, but you do not capture all these data characteristics. So these are some of the where the highest risk is that highest risk should be in this point, minus alpha by beta. That should be the. So how do I identify the most riskier group? So basically, if you think that your data follow really this type of model, then you try to find out this part, and those group which are in this value, they are the most risky people to give the loan or whatever you do. So that's the way you identify. So those people who will be working in insurance business or risk calculation business, you really need to know logistic regression really, really well. Otherwise, you will be always just a data analyst. You cannot be the manager. So let me skip rather than one small example. This is not risk analysis example. This is from the ecological study. What some of these scientists, they have the interest that those who are particularly working on the ecosystems, they're trying some specific type of crab, and it's, I think, yellow crab or whatever the crab, I forgot. The whole story, the long story short is that oftentimes in a particular season, that when there is a female crab, then there could be a male crab, but depends on the characteristics of the female crab. It might be 1, 2, 3, and why they like to know? They like to know the how the way this particular species is growing in that particular area for the ecosystem purposes. So that's what it is useful study for the biological scientist. So they like to see what really matters when some of the male crabs will be satellite with some of the female crabs. And they collect some of this data for the female crabs. So it will depend on the female crab's characteristics, right? So what the response, whether the male crab will come to the female crab or not, right? That's a qualitative characteristics. You can do it 1, 0 in that way. Or if they come, how many of them will come? Then it will be number. So the characteristics of the female crabs, there are some spine conditions, width and weight, and number of other variables are there. Okay, so number of others. So width means how much their width of that female crab or leg of the female crab. So these are this measurement. Okay, so how can you help this scientist that tell me whether these characteristics, how it is related to the whether a male crab will come to the female crab or not? What's the probability that if the female crab's width is 22.2, what's the probability that there would be a male crab? How do you do that? So here I have a little bit more description. See the color of the crab, light, medium, medium. Again, all are coded. All are coded because most of the data collected in this way also coded. It's not really the numeric. S is the spine condition. 1 is both good, 2 is worse, and W is carapace width in centimeter. Weight is weight in kg. And there also, like many female crab might have a more than one satellite, so many more. But we are interested in whether they have one or not. That's the thing at this point we like to know. So objective is to factor that affects with whether the female crab had any other males called satellites residing nearby. All this, forget it, all parts. So first thing you have to do, all this define that your response variable. Again, this is a notation, but not really in real sense it is these random variables, but you are making it a random variables. Particularly here you are making a binary random variables. X is the female crabs. As I said, that we will confine only one characteristics. So how X is related to the Y, but since it is coded variables, you will be making a relationship, the probability that Y equals to 1, which is your pi, with the X, or the proportion of 1, that is the mean, with this X. That's what you will be doing, right? Proportion of 1 would be the mean of the Y. So first thing, as you have learned in basic stat class, for this type of data you need some frequency table. How to do that? Since width is our interest, all different crabs has different width. Okay, so then basically you have in the record as many data point you have, that many widths may be differ. So your whole data can look much bigger. To look at in a summarized way, you do the frequency table, like width is less than 23.2 centimeter, then this 23.25, in this way a certain class. That gives you to see little better way. So still what is our interest? Our interest actually not with the interval rather than the exact value of the x. We like to calculate what the risk or what the probability that the female crab will have a satellite. Not so this is just to look at the data, but this data you cannot use, right? This is an interval data you cannot use. Everybody is getting my point, right? So how should I use, how should I fit the model? And just look at the things. Go back to your regression class day 2. First see whether this thing could be related, what we like to know, the proportion of this thing. These are the mean in this class, these are the mean in this class. So what is this thing? That means the crabs whose space length was less than 23.25 centimeter, 36% of them has at least one satellite. So these are the kind of the mean in this different class, and we are relating this thing with the mean. So from here you have to understand whether there is a regression. So you can do little bit of plot data visualization here, and you might see some kind of relationship. Okay, but without doing any regression, any modeling, some of the basic statistics you can calculate immediately. If I don't have the model, just like that our aspirin example. By the way, I should have gone back to the aspirin immediately, because I'll just remind me that you can do the similar modeling for this aspirin problem as well. So here is the probability that you like to know what's the probability that a female crab whose width space is certain x centimeter, what's the probability that she will have a satellite? So from here, so when you get a new number like x equal to, say you like to say, I have a female crab whose width space is say 25 centimeter. Tell me what's the probability that she will have, this crab will have a satellite. How do you do that? You look at that 25, where this 25 belongs. So probably it belongs within this group. So the probability should be sample proportion 61% is the probability that a female crab with width 25 centimeter will have a satellite, right? So this gives you actually probability calculation, again all this different way. But if I don't have even this type of data, that means even this data I don't have, I would have used the grand mean. So grand mean means I will just calculate the whole proportion. That would have been my probability. But once I have this information, at least this would be little better answer than using the grand mean, right? But still this is an approximate answer, because this x, the 25 centimeter belongs to this group. Can I improve my answer even more? So what I'm trying to say, let me repeat, probably I'm making you a little bit confusing. What I'm saying, if I didn't have this thing and I wanted to know what's the probability that a female crab whose width space is 25 centimeter, what's the probability that she will have a satellite? If I didn't have this data, what my answer would have been? I will calculate the grand proportion. That is the only answer I would have. And then if I ask you, what's the probability that if a female crab's legs width is say 27 centimeter, what's the probability that she will have a satellite? What should have been the answer? Same answer, because you don't have this data, you will get the same answer. Whatever the question you make, you have this mean, that is only you are using for the prediction. But if I have this one, I'm using now only this class information, because 25 in this class and then 27 belongs in this class, then we'll be using this class. And in that way, because what is the idea of the regression means, you are thinking that the mean is changing due to different values of the x. So you will try to, again, go to the idea of even nearest neighbor type of thing. Then you will be using the nearest neighbor of 25, and then you will try to find the answer from here. So you can use kind of So this is what I just said. This is nothing but idea of, I'm using the idea of k nearest neighbor idea, and then that's the answer you'll get, and that would be better answer for sure. Okay? But that may not be the optimal answer, because I like to know exact probability for exact value of x. Then what I can do, we can actually, instead of finding the class by class probability, I can combine all these class, try to find a smooth function which would be valid for any values of x, which from range from bottom range to top range. If I could do that, what are the things would happen? Two things will happen. First thing, you will see some of the improvement here, because you are no longer using the sample proportions. And another thing what you will see, when you have used this one, what was the variance? Variance would have been this time 1 minus this divided by number of things. That's the way the binomial variance you will be using, right? But if I use the model, it will combine all of them. So by combining all of them, what would happen? So let me make sure or try to reach you in this way. If I am trying to find an answer each class by class basis, then what you are having? You are estimating one mean here, one mean here, one mean here, in this way 1, 2, 3, 4, 5, 6, 7, 8. Even if you do the say k nearest neighborhood type of thing, you are estimating 8 means, right? If I combine all of this thing using my logistic regression, whatever we just studied, how many parameters are there? 2, because you have only one x alpha plus beta x, because that's what you are modeling the mean. So you will be estimating only 2 parameters. But if I don't do the modeling, I have to estimate 8 different parameters. But now I will be estimating only 2 parameters, and I will be able to predict the probability at any point. But since I am estimating only 2 parameters instead of 8 parameters, my model stability would be much higher. In other sense, my model variance would be much lower. As a result, your estimated variance would be much lower. So that's why another reason you have to do the modeling as well. So there are few different things I just tried to say. One, from the data perspective, you have to think about. Second thing is that by doing this way, you cannot get any concrete answer for a specific x. But if your assumed model follow kind of mimicking that right data, of course your model has to be right. If your model reflects the data right way, then I am estimating very few parameters, so my model stability is much higher. As a result, my risk of the risk is much lower. Variance of probability, estimated probabilities would be much lower. Make sense? Statistically makes sense? So that's the way you should do. And then basically the next part is very easy. You just put I would say that you do all this part here is so since you guys asked me the code is very simple. You put GLM y tilde x family equal to binomial, you will get the answer. And then if you like to have the confidence interval, etc., you can get it. Okay, I'm just suppressing this part, but it is easy to. But one thing, once you are very much comfortable with all these things, sometimes you like to write down how the way the estimating equations coming up. Like, what do I mean by that? Like when you did the least square, you know something called the normal equations. How this normal equation looks like here, and why you have to go iterative solutions. Because that's kind of the generality of the least square type of thing. So one should try to understand. Okay? Clear now what is logistic and how really it's becoming very powerful tool. It can answer much more with higher stability. You can calculate the risk for any point, of course within the range. So for this particular problem, we got the answer, right? Now, as I said, what if I did not attend this lecture and I attend just 2 days ago the linear regression? What I would have done? I would have just, this is again for the mean. I understand regression very well. So that's why the regression, the mean, and then I will have alpha plus beta x, right? I can run these things, as I said, that because I gave you the data, you can run all this part. You can do the maximum likelihood fitting or least square fitting. If you do that, you get this answer. So again, you can see that it kind of makes sense because this is the rate of change in the risk. If this is your risk for the different values of the x, that means by this way I know if I change the length of the width, what's the probability that change in the that having the satellite or not. Okay, so you can do this thing. We have the code as well. So what is wrong?
Basically, I'm trying to fit something between 0 to 1 to a whole real line.
But whole real line, that's a theoretical concept. It fitted this thing. So alpha and beta, you're theoretically minus infinity to plus infinity. But in practice, it could be any small value. Even alpha could be 0. Beta could be 0, right?
So, but this 5 hat will be always like 0.
Right.
But this right hand side
Might, but it might. So because mathematically it is could be minus infinity, but here it did not. So what is wrong? As a practitioner, so when I do this part, I did not take the math class, so I did not go to IIT, but I should be able to solve this problem for sure. So what is wrong? As I said, there are two different ways we are thinking. One, definitely the mathematical part we did not think about here. That's what we did solve this part. So if you have a math background, immediately you will say that this is wrong. But if you do not have the math background, still I would say that this is sensible result. It is not bad result because we have already I showed you the logistic regression that where you have a positive slope. So here also you get a positive slope. But what is the logistic characteristic was that the slope would change as the different risk factors, right? For this particular problem, we actually did not discuss even how the way risk changes at the different values of the risk factor. Here risk factor is the x. We did not even talk about. So first thing we have to understand how do I gave the example of your that credit fault or loan thing or buying a new product. That's pretty easy to understand. But when you have the data, then you should try to have some visualization process to understand really how the way risk changes. If it is changes, that risk changes different rate at the different values of x, then without knowing the mathematics even, I would say that this is wrong. Because it really does. So when the result is true, as I have been keep saying, if your model reflects the data well, whatever your model is, only you should believe on this thing. If your model does not reflect the data well, even mathematically it looks right, it may give you the garbage result. This whole interpretation may not be right exactly. That means if you are reporting that there is a chance or the probability increase about 9% by 1 centimeter increase in the Carrot space width, it may be wrong. Okay, because we don't have the validation of this part. So that's the way we should try to validate. On the other hand, also you can try to get the predicted value at the different possible values of x for a given context, because where the regression would be effective, you cannot take that x value completely from the other domain, right? You have to have a region where your data actually is. So what I can do immediately, I try to predict that risk, like the probability for the different values of x within the range of my data size, right? At least I can do that part. So if I do this thing, so far as I said there is no contradicting, possibly not. How about you predict this thing at the maximum with x equal to 33.5. Note that with alpha equal to this beta equal to this 33, this value is still right side would be not be infinity. But what happened? It is become 1.3. Then you are saying that you are calculating the risk becomes 1.3. That does not make sense. So in that sense, now you might say that something is wrong procedure wise. But otherwise, at the beginning, it didn't seem, to me at least, it was not that bad. And if I just wanted to know whether there is a positive relationship or not, I think I didn't have to do the logistic regression, because both the things tells me there is a positive relationship. But what's the strength of the relationship? When you are measuring that part, then there is an issue. If you are doing this linear regression type, that measurement, what you are getting, that strength of the measurement is wrong. And that's you are trying to reflect here, that this may be wrong, and that's why it may be wrong. And another thing, as I said, that you try to do the visualization, how the way risk changes, and whether that has been captured. Because when we have done that linear regression, the first thing we have done, plot the data and try to see the trend. So here, why did I show you? So that was a little bit surprising. Nobody asked me. There is a reason why did I show you this thing. From this one, you can plot the data and try to understand how the way risk changes for the different values of the x. And you would have seen possibly the logistic type of curve right here. As a result, right from the beginning, if you are a good data scientist, you would not even try the linear regression. And then, if you would not have tried this linear regression, then the contradiction would not have happened. Okay? All right. Make sense? Very good. So now you are the master of logistic regression. I'll skip all this part. You can fit this thing. I gave you the code. Then you can find the fitted line. Everything you can do that. Where the maximum changes, all these things, as I said, therefore, particularly these things are very important if you are working in the risk business or risk analysis industry. Then it is definitely useful. Okay, let me finish with one or two more examples. So again, response is a qualitative things. People are surveying, like you know that European Unions, there are still number of countries who wants to get into the European Union, and there are some of the countries which likes to get out of the European Union, but government takes the decision based on the vote. So there is a survey what you like. So entry, whether you favor yes or no. And two countries I can name you, like United Kingdom wanted to get out, and Turkey wants to get in. All sorts of things are there. And now probably number of other countries like to get out. So there are few of the factors that those are who are political scientists, because these things are also useful in political science as well. They think, again, this is a made up type of thing that already we think these are important, but in reality you have to really look for which of the variables would be important. Union member or not, when the guy who are taking the survey, whether he or she belongs to working class or not, then what is your schooling, and some of the other informations are there. So how do you do this modeling? You can immediately think about, since we have been doing this logistic regression, this one yes or no, and you can do this multiple things. But so in terms of running the code, there is nothing more to do other than running the code. But in terms of parameter interpretations, one has to be very, very careful. Okay? Particularly, this problem would be okay. Now, if you have some of the features which are also coded variables, then it becomes a lot more complicated. So doing the coding is pretty easy, but once you have the coded variable, interpretation could be much more difficult. By the way, so for this aspirin problem, how do I do this logistic regression? I wanted to know that odd, right? Or log odd. So how do I do this logistic regression? Your y would be still yes or no, whether you have a heart attack or not. what should be your X?
Whether you take aspirin or
You can, and that again, that's note that is also not a quantitative variable, it's a qualitative variables, and you code it 1 and 0. And if you do that thing, that X equal to also 1 and 0, Y is 1 and 0, and then in this formula, when you are writing this way, so this guy actually would represent whatever we already calculated, but if you fit these things with X equal to 1, 0, this is the odd, already we calculated the odd, same number you will get e power beta. And then X actually taking value 0 to 1, so what is this thing is saying, what is the change in the risk or the relative risk if your risk factor moves from one level up. So if you look at this thing, then you just put X to X plus 1 and then take the ratio, that would be odd ratio, then this factor will go out, and then this would be X plus 1 and plus 1, another thing will go out, will be deleted, so it would be eventually e power beta. So what I said, you change the X risk factor X to X plus 1. So that's the next level of risk, right? Then take ratio of this guy to the X plus 1, or X plus 1 to this guy. Then what would happen? Immediately this cancelled out, and here one would be X plus 1, another would be X, so e power X will cancel out, so it will be e power beta. So what does it mean? That means odd ratio is nothing but your e power beta. So if I fit a logistic regression, then e power beta would be same as odd ratio. By the way, who loves to code, that the Aspirin table summarized data what I gave, can you code it in R to fit a logistic regression? You do it. So anyway, so what I'm trying to say that oftentimes that proportions what we talked about, you can try to understand everything in a more general version in this way. Because all this odd calculus and everything can get more complicated if you have more categories, right? But if you can do everything in a regression aspect, then all category you can do coded way, and then what you can have this type of beta x plus beta 2x, all these things, then easy to run. So in terms of practice, it becomes really easy to implement. But what would be the complication would be the interpretations. Okay, so everybody is getting the point. So there is a trade-off between modeling versus non-modeling, but nevertheless modeling has lots of statistical advantage as well as computational advantage. Okay, all right. So this is the probably in the market research, this some of you might be interested in. There is a new AT&T is a, you can see this is a dated example, but right now you guys have too many phone company, like not Verizon, you don't have Vodafone, this, that, and then Ambani's has everyday new plan, all sorts of things, right? So this type of survey is very, very important. So objective is that, say you change AT&T to Ambani's Reliance. So in fact AT&T is not doing that good. AT&T is interested if the adoption of a new telecommunication service is related to the education, residential stability and income. This you can think about that new cell phone like iPhone comes into the market, whether a person will buy or not, it can depend on education, because even some people has huge money, they may not buy this iPhone X because it's a technical thing. Residential stability, if you are moving too much, again you may not buy this type of phone, all sorts of. This would be factor. Okay, here is a good thing. This could be factor when you are talking about landline. This may not be a factor when you are talking about this cell phone line. So you can do these things for two different survey, and you'll see that what the differences is, and that could make sense or not. Of course, income will make a. So it's a survey data. If you do the survey data, that you have to always summarize, because you cannot work with, if you suppose doing the survey with 2,000 clients or 20,000 people, they give it to me, I cannot do anything, but the data will come essentially some kind of summarized way. So 3 factors were there, right? School education, again, you are coding these things. Most of the cases you told me even all these variables are coded, right, in your survey. High school or below, some college or above. Then under this category, people are changing whether they have changed any phone line in last 5 years or not. Under this category, they have changed their phone line in last 5 years or not. Then this is the income group, low income group, high income group. You can have even others. And this is the whole data. In US context, this type of data was very useful because there are always multiple phone companies. In the past, India didn't have, that's why this survey was not making any sense, because everybody has to go to the government, then they would get it. But now you have too many choices. So this market survey, they have to do it. Before they launch anything, they have to do it. So the survey looks like this. So what I like to know, basically I like to know the odd under all different groups. So how many total groups would be? You have classification, you see that here is one, under one there is another one, there is another one. So for example, I like to know what's the odd that a person who has a high school education, who did not change his phone line in last 5 years, who belongs to the middle high income group, what's the odd that he will buy my new phone? So this type of picture gives you really, I think, in detailed story about the market, not just what's the probability that a person will buy your phone, the different segmentation of the populations like low income group, high educated group. I don't need to have all these crossed together. I might be interested only high educated group. Then actually I have to do some summing here. I might be interested in one cell. I might be interested in this cell. So that means I might be interested in different sector by sector, or I might be interested in only one sector, all sorts of things. How would I do that?
So we can model it, the output will be whether you have bought the phone or not bought the phone, and the various subparameters that we like to information history of quality education, history education, and the income.
How do you code it? So how many factors? So let's do that. So suppose you put here the code, you put high school education versus below 1 or 0. Okay, so then how do I do this?
College is again.
So it would be separate variable. So then I have one x1 factor, I have x2 factor.
X2 will be the income one.
No, x2 here already you need 2. X1 is the high school or below. X2 is some college or above. Already you have 2. Or you'd like to do it by in 1. If you have this 2, then under this, you have again 1 here, again 1 here. How do you do that? If I give you the answer, you might see that well. But if I don't give you the answer, I'm pretty sure it's not obvious. You cannot. So what you have to do, you have to have an indicator for each cell. So how many cells first here you have? You can think about how many total cells are here. It is not really all nested. There will be some of the cross, some of this nested. So you create first, you have to define the variables such that say 3 or 4 or 5 variables can identify all these cells. So in other words, eventually for each cell, I will have only one variable, one regression parameter has to define. So you define basically a regression model for which each cell will have one regression parameter. Everybody is clear my point, right? So as I said that I'll definitely do this thing, but in what I'm trying to make you say, unless you really clearly understand it, is coding even itself could be a problem, big problem. After doing this thing, I can hire even a undergraduate stat student. I'll ask him to run these things. He can do that part. For that, we don't need a PhD statistician or even PhD data scientist. We don't need. So here is one option. Some of these features that overall adapt. If you are interested in what's the probability any person will buy a new phone, as I said, always your grand mean. This is, you can see that how the way I'm saying. Always your grand mean is the starting answer. It is not the best answer, but that is not a wrong answer. It is, you might say that is the most inefficient answer, but that is not a wrong answer. But then what you see actually, since you got the number for each cell, then you can calculate the proportion like the way we did for the other example. You can calculate the proportion in each cell, and that can vary from 0.069, 0.270. So this might also gives you some idea how the way it changes the probability to different cells to cell. So what does it mean? That means we should not, so once it is true, then we should not, it immediately saying that if I use this grand mean as my answer, this is the definitely worst answer because already this data is suggesting this part. If this was fairly constant, I bet you, no matter whatever you do the modeling, your grand mean would be kind of the good answer. So before I do the modeling, because modeling needs lots of things, you need to do some of these things. And now, big story short, that's it. See, if we have to do the modeling, we just learn this regression, logistic regression. Then question is, how do we do that? I told you that you can, if you can think about logistic regression, but the most critical part would be how to define the predictor variables here. It could be very, unless you are very systematic, you might be in trouble, but how the way it is done, you can see that very simple. X1, it goes education, X2 is the no change, and X3 is the income. So for the three things, you can just define three part, and then you can, once you have this thing, it is pretty easy to run the R code, all this part, and then from X1 was education, X2 was last 5 years changes or not, X3 was, note that usually if you have, why it is important, I skipped that part. If you have three factors, usually you need to define two variables because three you cannot do that. But note that I here actually total three factors, but I have defined all these three because it takes care, each factor has even sub factors. That's why it took care of this whole non-identifiability issue. Okay, but otherwise if you follow that rule that if you have say 5 category, then you will put 4, that's the usual norm, because if you put the 5, then it would be non-identifiable. But here you have actually 3 of them. I did the 3, but it's not it is still identifiable because each class has the other factor. So now look at this thing, and you can try to interpret how the risk factor or what's the probability of adopting a new phone line changes depending on, so this one would change low income group to high income group. That means if you belong to low income, the odd of adopting an odd that a person who belongs to say high income group will adopt your AT&T new phone is about 16%. Odd that it's educated probably, that the person will add, or probably x2 equal to 1 or 0. In either way, I think this would be other way around, that odd that this was the last 5 years, that odd that who did not change their residency in the last 5 years, or that they will adopt these things is 0.01% only, which makes sense because if they are not changing the residency, why they will change the phone? The income would odd is about 44%, so which means that it is pretty much equally likely. So income probably does not matter much whether you will adopt the AT&T phone or not. But these two factors could be very important, whether you are changing your residency or not, and whether you are in a educated group or not. That matters much, whether you will adopt a new phone or not. So if I have to, then from simple analysis, if I have to give this idea to my management, what fact or what are the factors really people make a choice about your phone, really it is not their income, it is their residency status, and it is their education. That's the only things it matters. The others one doesn't matter much. Make sense? So if you can interpret this well, again the preliminary variable selections already you are done. And then nowadays you will be doing number of other things. All make sense? Okay, so all these things are there, but I think I will skip. Otherwise, it would be completely linear logistic regression class. So for sure, good. So we learned the logistic regression well, and you can see that still it is we can use as a classification. And next part, I'll do the classification where starting point even would be the logistic regression. We now know logistic regression well. So what I did not do that well in details, how to estimate this part, but it involved quite a bit. If you like to learn, you have to do. There are a number of codes available, number of different algorithms available. There is no unique algorithms, and all approximated solution. Unlike your linear regression, this is an approximated solution. And already I told you what should be the impact of that approximate, because variance formula, confidence interval, all based on asymptotic normality. So that's why still there is a time to time, although this is kind of a dead research area, but those who are working in industry and others, it is not a dead research area, dead area of research, and really targeting the practical problem. If you solve it with the theoretical things, it can publish in annals. And this is the recent example that in 2003 or 2009 there was an annals paper based on all these things. How to correct if I have this small sample. Because very important in the particular in drug industry, as I said, that when you have the third stage, fourth stage of the drug testing thing, you are doing on the 10, 12 people. You cannot allow any inverse bias in your estimate. No way. But what should be the reason is that why this answer, even if you know lots of mathematics, why you did it may not help. Just expansion after expansion usually increase the variance of your estimator. So it might correct some of the bias, but it will increase the variance. So there should be other way. So you have to be very innovative way to fix this problem, the bias correction, such that the final estimator would have still less bias, but less variance and less bias. Okay, all right. I think you got some good idea about this thing. So let's take a short break and then we'll be back here. Yes. Yes.
So the whole the crux of this problem lies in the sigmoid curve, right? Or say the logistic curve. So if I can plug in some other function which has similar properties with the sigmoid curve, let's say probit function. So there is this probit regression as well. So my question is, why this probit regression is not as popular as logistic regression? What is the drawback? I mean,
that's a good question. But first thing is that probit also will have that biased estimate. So you cannot get this unbiased estimate. Okay, because nonlinear link. Because of the nonlinearity, that bias correction you can do with one step Taylor expansion. So that is, but so that's, as you said, that's kind of this similar way. But the interpretation, as the way it goes, so without doing the model, I was telling you what's called the odds, right? What are the log odds? Then the log odds becomes a natural parameter under the logistic regression. I showed you, right? E power beta, or beta is the log odd. E power beta is the odd ratio. So log odd ratio should be the beta. So it's a natural from the model. If I do the logistic model, then what I am interested in, that log odd ratio, that becomes a natural parameter from the model. But if I would do the probit model, then there is no such natural parameter which would represent the log odd ratio. And log odd ratio is heavily used in social science, in medicine, everywhere. Doctors like to love this. If you ask them what is the risk, that they would say, I think odd is like this. They never, so what they understand also the log odd. So logit model gives the parameter which is natural connection with this log odds, but probit doesn't have. But probit has some of the other advantage. Computationally, actually, probit is much better. So econometricians use actually more probit than logit. but the medical science, marketing people, insurance people, they use much more logit than the probit. And the only reason is the risk calculation, and also the curve makes sense. What is the difference again the curve? Now think about, you know the logistic distribution itself. Think about the difference between logistic distribution and Gaussian distributions. In the tail area
is much like
because both of them in the middle part where the probability is 90% doesn't matter. Usually it will match, you can see. It will differ in the tail area, right? And where their interest is, because who I will be interested, the high risk factor group, they will be interested in. That's why logistic would be appropriate for them rather than the probit, because probit will have this tail area exactly Gaussian. So as a practical matter, logistic has lot more utility than the probit. Okay, makes sense? All right.